Hello everybody and welcome back to another visual pattern challenge. Here is our pattern today. Here's step 1, here's step 2, here's step 3. Your challenge is to predict the number of squares in step 4. If you can do that, can you predict the number in step 43? And can you write an equation that you could use to predict the number of squares in any step at all? So that's the challenge. If you'd like to accept it, pause the video and see what you can do. All right, well, we've got something interesting going on. There are these little pyramids with a door in them. I think what I'm going to do is just count the rows here and look at the rows. I think the rows are pretty regular. They grow by 2 each time, and we add a row each time, except that the bottom row has always got one missing, that little door in the pyramid. So here we've got a row of 1, and then the row of 3 with one missing below it, and then a 1, a 3, and then this would be a row of 5, except there's one missing. And then there's 1, 3, 5, and this would be 7, except there's one missing. So I think in step 4, I'm going to follow that same pattern and have 1, 3, 5, 7, and a row of 9, except one missing. So that would mean 8. So that's how I think step 4 is going to look. Let's add all that up. Let's see, 8 and 7 is 15, 20, 24 it looks like. So I think there are going to be 24 squares in step number 4. What kind of a pattern is this, actually? It looks like it's growing pretty rapidly, but let's analyze. So I'm going to put the step number in a chart and the number of squares as well, and we'll take a look at these numbers. So in step 1, we've got 3. In step 2, that is 8. In step 3, that is 15. And in step 4, we're predicting 24. So we can look at these numbers by taking the difference between each step. 8 minus 3 is 5, 15 minus 8 is 7, 24 minus 15 is 9. We didn't get a constant, so that means it's not a linear pattern. So we're going to go ahead and take the difference of the differences. 7 minus 5 is 2, and 9 minus 7 is 2. Aha! So a constant in the difference of the differences means x squared, and this 2 here means the coefficient of x squared is 1, so it's just an x squared and maybe some other stuff going on. What is that other stuff, though? Well, one approach might be to try to find the x squared and x those off and see what's left over. That's an approach that works. We've done that before. Another approach would be to look at these numbers and see if you can see anything that relates to x squared in them. There is something here that I'll point out later, but maybe it doesn't jump out at you. It's not super obvious. Another way to think about this, though, is something we've seen recently. When you have this sort of triangular looking shape where it goes up by the odd numbers, so 1 and 3 and, well, almost 5, and 1 and 3 and 5 and almost 7, that is the pattern that makes the squares. So how can we think about this? If I had 1, 3, 5, 7, this would be 4 squared because it's got those 4 odd numbers, successive odd numbers added together, but we're missing one. So this is step 3. So the square we're thinking about is really 1 beyond that. That would be x plus 1 squared. If this was filled in here. 1, 3, 5, 7, add all those together, you'd get 4 squared. But then we've got this one not filled in, so I would subtract 1. So I think this is my equation, this is my formula. Another way to look at that is with these numbers. If you're attuned to this, you might see that, well, 3 is 1 shy of 4, 8 is 1 shy of 9, 15 is 1 shy of 16, 24 1 shy of 25. So these are the squares, the perfect squares minus 1, and they're the perfect squares of one step up. So this is 2 squared minus 1, this is 3 squared minus 1, etc. And that's exactly what this up here expresses. The step number plus 1 squared, and then subtract 1 from it. So I think this equation is going to work. We'll test it in a second. And you can leave it in this form, but I'm going to go ahead and FOIL that out and see if we can simplify it. So let's see, FOILing out this part, I'd get x squared plus 2x plus 1, and then minus 1 from this minus 1 here. So this is really just x squared plus 2x. At this point, I'm going to take one further step and verify that visually. So here's an x squared, and that would be 2x's. This is 4, so there's an x squared, the step number squared. And oh, here's an x and here's an x. Yeah, this does seem to be working. So x squared plus 2x, I think we'll use that for our formula. Let's just verify with, let's say, step 2 to see that the numbers work out. So I would put in 2 and square it, plus 2 times 2. So that would be 4 plus 4, and that would be 8. That's what we got in step 2. How about step 3? That would be 3 squared plus 2 times 3, and that would be 9 plus 6. That's 15. Yeah, that's how many we got in step 3. So it does look like that's working. All right, the last thing to do then is just take step 43 and plug it in for x. So y equals 43 squared plus 2 times 43. 43 squared is 1,849, and 2 times 43 would be 86. So I'd get a 5 there, and a 3 there, and a 9 here. So I'm getting 1,935 squares in step 43. Well, how did that go for you? Did you see the perfect squares kind of hidden in these numbers? That's a little tricky to do. I'm curious if that jumped out at you. Or did you notice this pattern of odd numbers? When you add the odd numbers, you get the squares? Let me know. Thanks, everybody.